Hi, we are Team Quantum Robotics and we are proud to present our 2023 System Acceptance Review for the University Rover Challenge.
This season, we focused on improving our rover's core systems and our plan to successfully accomplish the competition missions.
We implemented a differential suspension system inspired by a rocky bogie.
This arrangement allows the rover to maintain its wheels in contact with the ground, while passing through irregular terrain such as inclined planes, rock, sand, and fragile structures without compromising the integrity of any subsystem.
The newly designed TPU Wheels gives outstanding traction and flexibility. In addition, the improved mechanical design based on bearings eases the assembly process and focuses on protecting the motor from critical collision.
The rover has a complete control power system that allows us to monitor the main voltage and the current given to each component, all secured with dedicated fuses per actuator. To ensure the integrity of the components, we incorporate a thermal circuit breaker that limits the given current up to 120 amperes as a kill switch.
We design our own PCBs in order to improve the component management, cells and wiring, and to connect interfaces used for some devices.
This allows us to fully trust the connection, therefore the communication protocols, as well as to reduce the size of the electronic components. We also connect a PCI card to increase the USB 3.0 ports.
We have been working with two omnidirectional antennas using the 900 MHz frequency, taking advantage of its long range and the performance of the MIMO system antennas. In our test, we managed to establish communication up to 800 meters away. Our base station is confirmed by three main computers in which we are able to visualize two real-time cameras, GPS navigation, and some metrics such as velocity, GPS position, battery status, and power consumption.
For autonomous navigation, we implemented the navigation stack along with an extended Kalman filter which fuses the odometry provided by the Z2 camera with the IMU sensors and the GPS odometry sources. We also used a Z-mini camera to publish laser scans measurements to avoid local objects detected.
Once the robot reaches the GNSS coordinate, it will perform different actions depending on the type of the goal. If there is no AR tag, the robot will stop and turn the matrix into a green blinking color. Otherwise, the robot will turn around its own axis at coordinates that create a mesh pattern, until our custom AR detector detects a new Aruco tag. For the final part, the robot will approach the tag, and in case the target type is a gate, it will surround the Aruco so that it eventually passes through the gates. The robot optimizes the time it spends on a mission by running Prim's algorithm over the coordinates to find the optimal path between them, and calculating the mesh coordinates that optimize the time that the robot spends looking for a tag.
We designed a 5 degrees of freedom robotic arm that allows us to fulfill tasks such as operating a joystick or pressing some buttons or writing on a keyboard, as well as carrying heavy objects as the 5-kilogram payload. We designed two kinds of gripper, one for precision tasks and one for the harder tasks that require heavy lifting. The one of precision has an inner silicon structure that deforms to correctly grab the material we are assigned.
The planetary gearboxes and worm gear mechanisms in our arm allow us to provide high-efficiency payload. Furthermore, they are implemented with a CAN protocol, which provides us with feedback from sensors to apply a closed-looped position controller. We perform a forward and inverse kinematics for our robotic arm that can be controlled by a graphic interface, combined with a teleoperated control, which allows us to move the end tool effector to specific positions. We also have a 2D arm visualizer to verify the position of each joint of the arm. With this, we achieved a practical and efficient way to perform all the manipulation tasks.
We chose a colorimetric-based analysis technique for a live detection method. For this, the mechanical system collects a soil sample to be directly disposed in test tubes preloaded with several reagents that will change color when detecting any of the four main molecules produced by known living organisms: proteins, lipids, polysaccharides, and carbohydrates.
In order to obtain a clear picture of the resulting color, the mixture goes to a centrifugation process, where the supernatant color is analyzed by a programmable color light frequency converter module. Further on, the results will be re-evaluated by the base station.